Okay, welcome everybody. Thank you very much for coming to today's seminar, which is going to be given by Elena Moretti. I have to give a little bit of an introduction because during last spring, we had here in the Institute Manuel Martinez, who was at that time the coordinator of the Cherenkov telescope array in Spain, and he was giving an introduction about the instrument that is being built in La Palma and Chile, and also about the contributions by MAGIC to the high energy community. Actually, at that time, he was telling about a nice result that was reported in the circulars, in astronomical circulars, about the first detection in the very high energy regime of a GRB. And this is actually what Elena is going to report here. And we are lucky today, actually, that she was one of the first and the main protagonists of this detection and the physics that has been gotten from the event. Okay, give an introduction about the speaker. Elena made her PhD in the University of Trieste, yes, in 2010, and since then she has been working in several high-level institutes, like they have it here, the KTH in Stockholm and the Max Planck Institute for Physics in Munich, and she's now based in IFAE, in the Institute of High Energy Physics in Barcelona. She has had a couple of very prestigious fellowships, like the Oscar Klein Fellowship, and she holds now a Marie Curie Fellowship in IFAE. And well, she's a well-known expert on gamma ray bursts and on the high energy and very high energy regime. On her CV, she has around 100 refereed publications and more than 10,000 citations in total, which speaks a lot about her profile in astrophysics, and she has been the leading author of many publications that are some of the most cited publications in her field. Okay, so today she's going to talk about the inverse Compton emission as revealed by very high energy observations by MAGIC, and yeah, first.
Thank you very much for having me here, and hello everyone. Let me restart the counter so I can. So yes, as Ivan just told you, I'm going to present the results of quite an important observation and detection that we made with MAGIC, which is a Cherenkov telescope, at the beginning of this year, so 2019, January 14th. Which is the way the GRB are normally called, by the date that they have been announced. So the results that I'm going to present here, they are explained and proposed in the two papers, which came out quite recently, last Thursday, and you can find there more details on what I'm going to explain. First of all, I would like to introduce some features and some properties of the GRBs. GRBs are gamma ray bursts, and they are quite bright sources. Here you see one of the first instruments that detect them, and at a certain point it gets saturated from the flux of the photons it receives. They occur more or less once per day. They are not repeatable sources, so to say, and they are serendipitous. We never know when and where they will explode in the sky. They are of cosmological origin, so they are distributed uniformly in the sky, and their observed flux is more or less 10 to the minus 5 erg per centimeter squared per second, for a total energy emitted of about 10 to the 52 or 53 erg. And the bulk of the emission, it's normally in MeV, mega electron volt. So they are constituted of two phases. We name them prompt phase, which is a very impulsive phase and highly variable, and it lasts for hundreds of seconds. This prompt phase, it can last up to hundreds of seconds. And the second phase, that is called afterglow, that is a slowly decaying phase, and it can last for thousands of seconds and days and so on. Depending on the duration of this prompt phase, they are catalogued in two different types. Here you see the distribution of this, the duration of this prompt phase. There are short gamma ray bursts up to 2 seconds, and there are long gamma ray bursts up to thousands of seconds, around 1,000 of seconds. This too is not just a way to catalog them, but it's connected with their progenitor. So what is the object that emit this kind of bursts? The short ones are connected, and we had recently the proof with the detection, detection at the same time of a GRB and a gamma ray and a gravitational wave coming from the merging of a binary system of compact objects, while the long ones are connected with the death of a massive star. So, but independently of their progenitor, the gravitational potential energy that is in this system is then transformed into kinetic energy, and from kinetic energy is dissipated into photons, and from gamma mostly, and then up to optical and radio. Here you see a cartoon of how this happens. You have here the central engine, and then the central engine emits blobs of plasma, and these blobs are emitted at different times and with different velocities. When the blobs interact with each other, one overcomes the other, and they interact with each other. In this phase, there are some internal shocks, and in these internal shocks there are the acceleration of particles from where then the gamma rays are emitted. This is thought to be the mechanism for generating the prompt phase, while the afterglow phase is generated when this plasma is interacted with the interstellar medium outside via forward shock. And in this forward shock, again, there are acceleration of particles. And from here, we have a more wide emission from radio to X and gamma. Sorry. From the point of view of the spectrum, of the spectra, they are very much similar to each other. In particular, in the prompt phase, here you see a spectrum of the prompt phase, and you see it's quite featureless except for a general peak in the middle of the energy band. And there are some theories for the interpretation of the spectra. Some theoreticians say that they are coming from synchrotron emission. Some think that there is still a thermal component, and so finally this part is still not resolved. While there is a more general agreement on the spectrum of the afterglow phase. The afterglow phase is normally explained via synchrotron emission, and here you have an example of a modeling of a prediction very long ago of afterglow spectrum, and then you can see from all this spectrum that there are several breaks in the spectrum, and we try, once we look at the observation, to reconstruct these breaks and the slopes between the breaks, and the time evolution that you have here depends very much on the parental distribution of the electrons, and of the and or the interstellar medium, where the kind of interstellar medium and environment where this shock happens. Sorry, I have some problems with my voice. Still recently, we had the detection. This was the past record breaker GRB. This was detected by Fermilab. Actually, this is the publication from Fermilab. And this GRB, 1304-27A, was holding the record for the highest energy photon that was ever seen. And as you can see, most probably this photon, which is this one, is coming during the afterglow phase. And in the interpretation of synchrotron emission with different kind of environments, you see here these are these kind of different curves. It depends on the environment we model. This is the synchrotron limit, so to say. So how much energy can synchrotron emit? And as you can see, with a very extreme hypothesis of the environment, we still can justify this energy from the photon. So the picture before the detection that I'm going to tell you about now is it was confirmed to be synchrotron. There was no disproof of it. And even more, this is from work we did for Fermilab. This is the catalog of the 10-year catalog from GRB seen by Fermilab. And here you can see the maximum photon energy that has been recorded by Fermilab for each GRB, and the time since the time they were emitted. And this is in the units of sorry, of prompt or the duration of the prompt emission. As you can see, this is more or less the band where Cherenkov telescope can detect these GRBs. I explain you a little bit better. This is the energy threshold around, I put it here around, sorry, around 50 GeV, the energy threshold for Cherenkov telescopes. And then I took more or less 100 seconds, okay? So up here, as you can see, there are very few photons. So the prospects for detecting this kind of the GRBs were very, very slim, given from 10 years of observation of Fermilab. Indeed, this, what I'm going to tell you, was a search of more than 20 years from Cherenkov telescopes. As you can see, we look at the we observe GRBs in all the wavelengths, from radio up to gamma rays, and here it's missing, but also in Cherenkov, which is even higher than the energy that LAT observes. Sorry. I'm sorry. So as I told you, this energy range is covered by Cherenkov telescopes that are telescopes on ground. They look at the Cherenkov light emitted by the shower caused by the incoming gamma. And one of them is MAGIC. Here you can see a picture of MAGIC. MAGIC is a system of 2 Cherenkov telescopes that image this kind of showers, and from the characteristics of the shower can reconstruct the incoming photon in the atmosphere, in the energy. The two MAGIC were built and thought, so designed to be able to repoint very quickly in 30 seconds, exactly for the purpose of catching a GRB in the prompt phase. So a big effort was made in the design of this kind of telescopes. The other two experiments that work in Cherenkov astronomy don't have these properties. While MAGIC was thought and designed for this. But now you can see, for example, how is movement for catching the GRBs. You can see here the two MAGICs that are going to be repointed. This is actually not the fastest. This is almost the fastest movement. And as you, these two telescopes are almost 64 tons each. They are impressive to be repointed in 30 seconds. The oh, sorry, I missed. Okay. Then we do this. MAGIC has a certain system to be able to follow up GRBs. Sorry, because the repointing is the design of the repointing was a major achievement, but was not just the only piece of the puzzle to be able to follow GRB. Also, we need to be connected to the to the network of alerts that are given by satellites normally. So GCN, with the notice are called GCN. GCN comes and there is a software, a multi-threaded software that is trying to first select the object to observe, because not all the objects are observable by MAGIC. We have some, of course, cuts. Sorry, on the properties, on the position of this GRB, and then finally, if the alert is positive, if we follow up this alert, then we have to stop the data acquisition that we were doing, because it can happen at any time we are observing. Then we need to stop the acquisition, repointing, restart the acquisition. And so it's quite a big procedure to be done. And it costed a lot of work and several tests to be able to perform this way. Finally, we normally follow about 10 GRB per year. The duty cycle is more or less 10%. This is due to weather, to day and night, and to localization of the GRBs, how they come to us. So we go back. So what happened that night? That night, one of these notices came in at about 9 UTC. The notice was given by two satellites, the Swift-BAT and the Fermi GBM, and was received 22 seconds after by MAGIC. And 50 seconds after the beginning of the burst, MAGIC was already starting the data acquisition. So less than 1 minute, we were already on target and taking data. And mind that 22 seconds of this were lost into getting the message to our system. And you can see here the light curve, so the photon flux as a function of time of the burst seen by Swift-BAT. So it's a hard X-ray instrument, and you see here the prompt phase, the very highly variable prompt phase, while here this is the decaying phase, and you can see here when we started the data acquisition. That night, let me see. Yes, that night I was, by coincidence, I was in La Palma, where the MAGIC are, and sorry, I was there for another reason. I was there for the commissioning of another Cherenkov telescope that is called LSAT. That is one of the Cherenkov telescopes inside the CTA. And the commissioning, the shift leader of MAGIC that night sent me this picture that you see here, asking me if this was a test, because we know when someone from the GRB group is there, normally we test the crew and the system, and we send an alert to Crab, normally, or to Markarian in that period, and we tried to see if everything works, everything responds well. So the shift leader thought it was a test because I was around, and he sent me a picture saying, "Are you doing a test?" And I said, "No, I'm not doing any test, and nobody's doing any test." And so I ran to the counting house where we take the data of MAGIC, and I saw that actually, sorry, you cannot see very well, these are pictures taken with the phone, that we had a quite large flux of this object. It took me a while to convince myself that we were actually receiving real signal from GRBs. After more than 20 years of search, it was hard to think, yes, this is the time. But that night, we managed, after a couple of hours, to send out an alert to alert the rest of the community so that they could follow up and give more information from other wavelengths of this object. So let's start to have a look at the MAGIC signal. As I told you before, this is the signal seen as from another instrument. And MAGIC started the observation here. As you can see, MAGIC detected more or less the part of the slowly decaying phase, so the afterglow phase. In the first 30 seconds, more or less, of observation, this GRB was 100 times the flux of Crab. Crab is our standard candle, and is always detectable, and we see it very quickly. Indeed, this GRB is the brightest TeV source ever detected, and it is quite impressive, the signal. You can see here, oops, you can see here the level of the emission of the Crab. As a comparison, this is the emission, the emission that we have from the GRB. And for comparison, this is what we get from Crab Nebula. This is magnified by 3. So you see how slow it goes with respect to Crab. And also, you can see that Crab is quite a constant flux, while the GRB has an impulsive part, so it starts quite bright and then slowly decays. Thanks to this temporal properties, we are also studying, we're also thinking of putting an upper limit on the Lorentz invariance violation because of the high energy photons we received, and we can use the temporal properties of this object. But, sorry. Once we detect this signal, we would like to know what it is. We would like to understand where it comes from, how it comes, and how it's produced. So the first thing we do is look at the spectrum. And here you have the spectrum of what we saw. This in gray is the spectrum that MAGIC observed, so the spectrum that we got in our detector. But we know that this is a distant source, and the highest energy is absorbed by the background light. So once we know how the background light, we can deconvolve this spectrum and obtain the intrinsic spectrum that is emitted from the source. That is this blue. There are these blue points here. As you can see, sorry, I didn't say, the spectrum is the energy flux as a function of energy. As you can see, this is more or less a flat spectrum, which means that roughly the energy is equally distributed along all the energy band where we were observing. And if you compare this flux with the flux that is received at X-ray, hard X-rays, this is about half of that flux. So up to now, we lost half of the emission, half of the flux of the emission from this kind of sources. So now we looked a little bit at the spectrum, and now we look instead at the energy of this emission. If you remember before, I told you that we already compared the emission from the record breaker GRB with the synchrotron limit. So now we do the same exercise. Here we have the curves depending on the environment of the synchrotron limit. So the maximum energy that can be emitted via this process. These are curves as a function of time. And you see, this is the emission that we see with MAGIC. So it's far above the synchrotron limit. This clearly indicates that we are not seeing synchrotron anymore. We are seeing some other component. At least not synchrotron coming from leptons. So how about if we were seeing synchrotron coming from protons? Now protons, they can overcome this limit from the leptonic one because they are heavier and they can emit higher energies. And they are naturally present in the ejecta in the plasma that is emitted by the gamma ray burst. But if then we go and try to do the calculations for this kind of protons to be able to emit up to 1 TeV, we get quite constraining. We can constrain quite high the energy that should be put into these protons. And even more, the constraint is even higher if they would be responsible for the full flux that we see at this energy range. In particular, we put a limit that the proton should have more than 2 times 10 to the 59 erg, when I told you that 10 to the 52, 10 to the 53 erg is normally what we have. So it's 10 to the 6 times higher the energy that was normally emitted. So we exclude that it's a synchrotron from lepton, and we exclude that it's synchrotron from protons. Then, thanks to the data that were collected, we can have a look at this object, at this emission, from a larger perspective, so from a multi-wavelength perspective. Here you see the collection of data that we have from this, for this burst. You see the gray one is what we saw already. Then here we have LAT data and gamma ray data. These ones are the data from MAGIC, which is the slowly decaying phase. As I told you, it's called the early afterglow phase when we start to take the data. And here we have the radio data, and here we have the optical data. Among these, the optical data are the ones that Alberto collected with the GTC. So we know here that MAGIC data were collected at early afterglow phase, and we see that it has more or less the same decaying rate as the X-rays or the LAT data, as you can see here. So if we go back to the cartoon that I told you at the beginning about, it means that most probably the emission we are looking at, it's created in this part of the shocks. So in this part of the emission, where the ejecta shock against the interstellar medium. So it's produced in the same place where X-ray and gamma rays are produced, but it's not produced with the same mechanism. Because, as I told you, the X-ray and gamma rays are thought to be synchrotron. So we can have a look now at the spectrum again, but from a larger point of view, meaning that we take into account from X data to the magic data. This is the spectrum, and it's divided in time bins. The blue one is the first time bin from the 68 second to 100 second, and then it evolves into the yellow one, and then for the other time bins, we have data from magic, but not from the other wavelength. Here you can see the clear time evolution of the magic data. So it's slowly decaying in flux, but not much changing in spectrum, in the power law. Here you can see that we get an extra information, and this is an extra piece in our puzzle. We see that more or less this is one component, while magic does not belong to this component. The magic data must come, or the emission that magic has seen must come from another component, different from the one that is seen up to the LAT energy ranges. So it's created by, the emission is created at the same place, but not the same process. And what we think it is, this process, is inverse Compton, as you probably thought already at the beginning. Inverse Compton is a process where the photon gets more energy by the interaction with an electron. And we model it, this is a model, as a particular kind of inverse Compton that is called synchrotron self-Compton, where the photon that receives energy is the same photon that has been emitted in the synchrotron phase from the synchrotron emission. And if we, in this interpretation, we model the data, we can connect these two components. And in particular, by knowing the breaks in this part, we can reconstruct what would be the energy peak of the synchrotron self-Compton component. If we compare this calculation with what we see with magic, we found out that the energy peak would be much higher than the magic where the magic is constraining the data. So we model that there are other two processes that are acting and that are absorbing the high energy part of the spectrum. These two processes are the Klein-Schiene effect and the photon absorption, the gamma-gamma absorption, that absorb just the higher part of the spectrum. So if with this model, then we look into the temporal profile. This is an exercise we can do because if we know the dynamics, then we can model also the temporal profile. Now, this model is the one that you see in solid line, is optimized for the very high energy part of the spectrum. And as you can see, it has some limits because it doesn't describe very well the optical part and the radio part, the evolution in time. If instead we try to make it working for this part, which is the dashed lines, you see, for this wavelength, then it doesn't describe very well the high energy part. But this is maybe some problems in the model that we don't know perfectly. We cannot model it very well. So to summarize what we get from the model, we know that we can derive that the energy in the synchrotron component is about 10 to the 52 Hertz, while the energy in this other new component is about half of this energy emitted in the synchrotron component. And this is a large part of the energy computation, the total energy computation that we've lost up to now. While this is the first time we can put constraints on the magnetic field that must be there to be able to emit via synchrotron. And we see that the magnetic field is quite high if you have the idea of how much is microgauss normally in the interstellar medium. So there must be quite a big magnification of the magnetic field in act during these shocks. And then we can also constrain how much is the energy that goes into the magnetic field and how much is the energy into the electrons. Now, this is a parameter that is normally already reconstructed or constrained by the model only the synchrotron part, while this part is not. This is derived thanks to the interpretation of this new and to the study of this new component. This is quite a typical value for GRBs, and also the Baltzl-Lorenz factor that we derived for the ejecta. It's around 500, depends on the medium that we take into account, and also the total isotropic energy that is emitted from the GRB. These are the ones that it's not the first time that we constrain, are quite typical values that we've seen in other GRBs. So if we look at the intrinsic characteristic of this GRB, we see that it's quite a normal GRB. Indeed, if you look at it as a function of the energy that is emitted as a function of the redshift, you can see that it's a bright one, but not so bright. Okay, so it's just that it's close to us, but not so bright. So it's a quite, how you say, normal GRB. So why we managed to detect this one now and not all the others before? Indeed, we can say that we have quite an extraordinary instrument, because in that night we could observe, which is a particularity of MAGIC among all the Cherenkov telescopes, because there was moon, and MAGIC is now optimized also to be able to observe during moon. Now, moon observation at that time makes the noise level 6 times higher than the normal dark night noise level, and the zenith was quite large. So this part is coming. The possibility of observing is coming from our optimization of the instrument, which has been quite worked out during the years. And but then MAGIC is observing GRBs since 10 years and has collected more or less hundreds of observations. So if we go back and we select among these 100 the ones that have redshift less than 1, which is the universe that normally can be observed by MAGIC, and where we can repoint in less than 1 hour, we come up with only these 4 GRBs. Now, the first one was observed with only 1 MAGIC, was the time where MAGIC was only 1 telescope. The second one, we arrived at it quite late. The third one, which was still in moon, it's a short GRB, so normally they emit a little bit less energy. We have a 3 sigma hint from this GRB. And the fourth one is the one that we finally detected. So finally, the point where we have an exceptional part is that we were able to observe during moon time, and we get the luck that this GRB was quite close. So finally, to conclude, the observation was made possible, the detection was made possible by the capability of MAGIC to fast react, so to repoint quickly, and to be able to operate during moonlight, to observe during moonlight. I didn't say, before, but the signal only lasted for about 40 minutes, so it went off very quickly. We collected a very clean and almost background-free signal, and we could emit an alert quite rapidly. We got from this signal the first evidence for an extra component above the synchrotron, beyond synchrotron. And as you saw from the data that were collected on this burst, there was quite a high interest in this burst from the community. And we managed to model this emission with a unique model that explains all the data more or less from radio up to TeV. And thanks to this model, we find finally that this is a quite common GRB. And as I told you, the exceptional part is that we could operate during this phase, and that we could repoint rapidly, and that the GRB was close. So that's all. Thank you.
Thank you very much, Elena, for your nice talk. Are there any questions? I'm sure there are. Yeah, Alberto. Take the mic.
Wonderful talk, Elena. So, do we need to increase all the GRB energetics by a factor of 50% now, you think?
Yes, I think so. I think that this is a quite normal component, the synchrotron or the inverse Compton component. We'll see if it is really synchrotron self-Compton, but I believe it's quite a normal component that is present in the emission, and that is just that up to now we didn't manage to detect it, but yes, now we managed to detect it, and we get the confirmation that it's there, and finally. And then yes, we should start to model from now on the GRB, so all the modeling should take into account the extra energy budget and the presence in the spectrum of this component.
Is operating now 3 weeks a month, just always avoiding full moon, or is okay? So I think
it stops for days around full moon. Yes, it operates almost all the time that is left. In the days quite close to the moon, there is a part of night that we cannot operate. But MAGIC has the highest duty cycle among the Cherenkov telescopes, because the other two cannot observe during moon time. MAGIC only has worked this particular instrumentation and way of analyzing the data that works also during moon time. And this is particularly good for transient events. Any kind of transient events that you never know when they can happen, and you must be ready to take data, then we have a higher duty cycle with respect to the other Cherenkov telescopes. And this is an important point.
We expect to see new detections coming soon, I guess, hopefully.
If they collaborate, if they are close, we do our best.
Thank you. Okay, are there any other questions? Yes.
Well, I want to know how is CTA going to increase the detectability of these events?
So, as you know, CTA is composed by different sizes of the Cherenkov telescopes. One is the largest size, and once you make a large dish, you can collect more light, which means that you can go to a lower energy threshold. And we have already one of them, which is LST. And the prediction for this, for the detectability for CTA, are of about half a GRB per year. So you gain in energy because you lower the threshold, and you gain in field of view because the LST have a larger field of view. What you do not gain is the duty cycle, because they are positioned in exactly the same place. As night and day is always the same, weather is always the same, And so you have this, maybe you can gain a little bit also because you have a wider field of view into the cut that we make for the error in the position. So when we receive the alert, we need to make a cut in the error of the position because if the error is too large, we are not sure that we are going to point to the correct GRBs. While with a wider field of view, you can relax a little bit this cut, and so you gain also there.
Estimate made for the set of the 4 LST telescopes, or only for the first one?
4 of the 4 LST telescopes. Well, this estimate is actually made for the full CTA, but because it's driven by the LST, because the most important part is actually the energy threshold, is basically when you have the 4 LSTs there.
Are there more questions? I have myself one or perhaps two. So, well, in the Blazar community, a way that we have to try to disentangle between the different inverse quantum mechanism, either synchrotrons of Compton or external by other sources of photons, is to check the simultaneity of the variations at the different bands. I think you have the data for that. So did you make the test to check how much is the correlation between different bands to check?
We have the, oh, sorry, I'm going to the wrong way. We do not have variation in different bands because while in AGNs you can, you see a flare and then you see how much is this flare in the other bands. We don't have a flare. This is all we have. So if you move these parts a little bit higher or a little bit lower, it's the same decaying rate. So it's not that you can check what happens in this band if it reflects later in time in this other band. This is what is the difference for us. So we don't have variability here that we can cross-correlate between energy bands. We have only a slowly decaying phase.
Yeah, but you have shapes in that. Like, for example, the very high energy gamma ray 1 is relatively flat.
Okay.
Relatively straight line. Whereas, for example, in the optical, you have some brightening at the end and so on. So
this part here, the part of the optical is given by the reverse shock. I can show you here. I didn't explain this part of the reverse shock. It's this part here. So when you have the forward shock and the part of this shock is also reversed. And the contribution for this reverse shock is mostly in optical and in radio. And so they create in time a slightly different profile, time profile, because of the component that you get from this part. While the other energy bands do not have at least for this GRB, do not have the reverse shock component, and so they have more or less the same behavior.
The question was about the how did you discriminate? I think you explained that, but I missed it. How did you discriminate between the possibility of synchrotron emission from protons and inverse quantum? There was a plot there that you showed that the emission is not in the right place, but how is that plot?
So, this is the emission. The calculation of the emission from the synchrotron coming from leptons, so electrons. Okay. And these are the curves of the maximum energy as a function of time that can be emitted by electrons via synchrotron. So this is the leptonic side, so to say.
But I guess you consider protons.
And then only in proton, then the proton part, as I said, overcomes the part of the energy, but it does not overcome the part of the flux and the up to which energy it's emitting. So from these two other points, so arriving at more or less 1 TeV emission and maintaining or emitting the flux that we see with the GRB in this GRB, this one constrain a lot how much energy the proton population needs to have. And the second one, so the flux one, is quite large. A constraint is about 10 to the 6 times the energy that we see in this.
Clear. So more questions, perhaps? If not, then we thank our speaker again. Thank you very much.